Hi, welcome back to Transformer series. Today we are going to look into one specific structure inside Transformer, that is encoder layer. There is a difference between an encoder layer and encoder. You will soon see that. You will see that what goes inside this layer. What is the computation that goes in? What is the structure? You will also see why stacking 6 of them together gets us a complete encoder. So let's get started. I call them Lego brick, and it is not a metaphor. It is technically accurate. A Lego brick has a fixed interface. Pegs on top, holes on bottom, same dimensions every time. The encoder layer works the same way. Whatever shape of data goes in, exactly the same shape of comes out. The fixed interface is what lets you snap them together without any modification. Whether you use 2 layers or 96, doesn't matter. Here is what we will build up in this video. 2 sublayers. These are core computation. Then add a norm, the stabilization mechanism that wraps each sublayers. Then residual connection and layer norm, we will look at them separately because they do different jobs and deserve separate explanation. And finally, the difference between post-LN and pre-LN placement, because the small positional choice has a real consequences when you train a deep model. Before we look inside the layer in detail, let us establish the overall shape of the machine. You can see the outer border of one encoder layer on the screen now. X enters on the left, carrying all the token vectors of your sentence. Y exits on the right, carrying a refined version of those same token vectors. Everything that happens between X and Y is what this video is about. The first thing X encounters is self-attention sublayer. The label below it says group discussion, and that name is deliberate. Self-attention is the moment where every token in your sentence is allowed to look at every other token simultaneously. No token is processed in isolation here. The word cat and the word sat and the word mat, they all exchange information with each other before any individual processing begins. After the group discussion, each token goes into its own private room, that is feed forward sublayer. The label says private reflection, which is again precise. The feed forward network processes each token completely independently of every other token. What happens in group discussion shaped each token's representation, and now each token digests that new information entirely on its own. After each of those 2 sublayers, you will see a small box called add and norm. There are 2 of them, one after self-attention and one after feed forward. They are not for decoration. They perform 2 distinct operations. They add the original input back into the sublayer output through a residual connection, and they normalize the result to keep the numerical value stable. We'll look at each of these mechanisms in detail later in the video. Now watch the gold particle moving through the pipeline. It enters as X, passes through self-attention, is stabilized by the first add and norm, passes through feed forward, is again stabilized by the second add and norm, and exit as Y. That complete journey is one encoder layer. Every token in your sentence go through this exact sequence: group discussion, stabilize, private reflection, and then stabilize again. 2 sublayers, 4 operation in total. Okay, now we saw the overview. Now we are going to go into detail. We're going to see that each component, each element that we saw has a specific name, specific job to perform, and a specific order. We are going to build it component by component so that by the end of this slide, you will know what each component does and what is the order. So let's get started. X appears on the left. This is the input to the layer, a matrix of token vector. 1 row per word in your sentence. Each vector has a fixed number of dimension. In the original transformer paper, that number is 512. X is the entire sequence represented as a stack of real valued vector, and the matrix is what flows through the entire pipeline. The multi-head self-attention block that you see here, notice what's happening simultaneously. A gold arc draws above it along top of the diagram. The arc is the first residual connection, the bypass highway. X branches at this point. The main copy of X enters the self-attention block to be transformed. A second copy of X travel along the gold arc unchanged to be recombined on the other side. Both paths are alive at the same time. After self-attention produces its output, let's call it H, the two path meets at a plus circle. The original X which traveled along the bypass is added element-wise to the H, and then that sum passes through the first layer norm box, which normalizes it. The result is labeled as, let's say, X1. The first refined version of our token representation ready to continue into the next sublayer. Now X1 enters the feed forward sublayer and the identical pattern repeat. A second residual arc appears drawn below the diagram in teal. The input to this sublayer X1 branches out. Part of it goes through feed forward to be transformed. The copy travels around the bottom waiting to be added back to the far side. The same addition and normalization happens again. Feed forward's output is added to the bypassed X1 and the result is normalized by the second layer norm. And what exists on the right is Y. Y is of the same shape as X. The same number of token, the same number of dimension per token. The matching shape is what allows the next encoder layer to receive Y without any modification. The two formulas at the bottom captures the entire pipeline in the compact form. X1 equal to layer norm of X plus H. Add the bypass X to the self-attention output, that is H, and then normalize it. Y equal to layer norm of X1 plus F. Add the bypass X1 to the feed forward output F and then normalize again. Two formulas, two sublayers, and the structure of the full layer is complete. The term H in that first formula is what self-attention compute. We are now going to zoom into exactly one of the two boxes from the pipeline, the self-attention block, and watch H being produced on a real sentence. Here is a sentence: the cat sat on the mat. Each word has become a token, and each token is one box on the screen. At this moment in the encoder layer, self-attention is about to run. Every one of these 6 tokens will be transformed, and during that transformation, each token is allowed to look at every other token in the sentence simultaneously. Watch the arc draw out from SAT, which is now highlighted in gold and labeled query. Self-attention work by treating one token as query, the token asking the question, and computing how much attention it should pay to every other token. The arc from SAT to CAT is the thickest, meaning SAT pays the most attention to CAT when forming its new representation. The arc to MAT is moderately thick. The arc to the, on, and the second the are sort of thin. The legend in the corner confirms it. Arc thickness represents attention weight. Thicker means more influence. The formula reads as such: H equals multi-head self-attention of X. The word self in the name, it is important part. In cross-attention, which we will see in the decoder video, the queries come from one sentence and the keys and the values come from another. In self-attention, all 3 queries, key and values are computed from the same input X. The sentence is attending to itself. That is what allows SAT to gather information from CAT and MAT before either of them goes through the feed-forward processing. We saw the gold bypass arc in the pipeline diagram. Now we look at what it actually does and why removing it would make the training deep networks nearly impossible. X enters on the left. Notice the gold dot, that is the branch point. This is where the signal split. The main path carries X forward into the sublayer. A second path copies X exactly as it is, no transformation, no modification of any kind, and carries it separately around outside, right? Around outside the block. This copied signal is the residual connection. The sublayer receives the main path signal and produces the output. We are calling the output as H here. But this diagram may equally apply to feed-forward sublayer as well. In that case, the output would be F. What sublayer produce might be very informative, or it might be nearly random during the early training, right? When weights have not yet been tuned. H exists to the right, heading towards the plus circle. Now the bypass comes in, right? The gold arc carries the original X completely untouched across the entire width of the sublayer. The label identity highway is exact mathematical term, by the way. The bypass applies the identity function to X. Whatever X has was, that is precisely what arrives at the plus circle. At plus circle, the only operation that is performed is X plus H. It is not average, it is not any other operation. It is actually plus. If H contains useful information, this sum is going to get richer because X gets added. If H has noise, the sum will approximately be X, because X is the original matrix that we have. The model can still function because the original X arrived safely via the bypass highway. This is the protection the residual connection provides. The X plus H immediately passes through a layer norm, which we will examine in the next slide. The normalized result exists as X1. That is the complete residual sublayer computation. Add, bypass, normalize, and continue. The precise formula is actually given below. X is equal to layer norm of X plus dropout of H. The dropout term is a training time regularization. During training, some values in H are randomly zeroed out to prevent the model from over-relying on any one pathway. During inference, the dropout is switched off and H is used in full. The result of the formula exactly matches the diagram. Add the bypass to the sublayer output and then normalize. Now this is very important. This sentence is the reason residual connection exists. In the early stages of training, sublayer weights are essentially random. The sublayer will produce output that are nearly meaningless without any residual connection. And the meaningless output would be the only signal reaching into the next layer. The gradient would actually vanish before they could improve earlier weights. With the residual connection, the original X arrives at the next layer intact, regardless of what the sublayer currently produces. The model has a fallback. It can pass the input forward unchanged while the sublayer gradually learns to contribute something better. The residual addition produces X plus H. Before the sum moves forward, it passes through a layer normalization. Let us look at the specific problem layer norm is solving. On the left, you see 5 features from single token vector measured after the residual addition, but before normalization. Feature 1 is around 92%, feature 2 is 12%, feature 3 is 78%, feature 4 is 5%, feature 5 is 55%. Notice also that bars are trembling. That trembling represents the instability of these values as training continues. Feature at widely different scale produce gradient of widely different size, which makes the learning process chaotic and slow. Layer normalization exists specifically to correct this. After layer normalization, look at the right panel. Feature 1 is at 55, feature 2 is at 48, feature 3 is at 52, feature 4 is at 45, feature 5 is at 50. The values are moved from a range spanning from 5% to 92% down to a tight cluster between 45 and 55. The bars are stable. Layer norm subtract the mean of the vector and divide it by standard deviation, recentering the output around 0. compressing the scale to a variance of approximately 1. Then it applied a learned rescaling to put the values in a range that works well for the next sublayer. And this formula is exactly telling that x hat I equals xi minus mu divided by sigma plus epsilon multiplied by gamma plus beta. Let's look at this formula piece by piece. The xi minus mu subtract the mean of the vector, right? So what does it do? It is centering it at 0. Dividing by sigma plus epsilon, that is divide by standard deviation. Epsilon is a very small number here, added only to prevent division by 0 when sigma actually is approaching 0. This subtraction and division together produce a 0 mean unit variance vector. Then the gamma and beta are applied. Gamma is a learned scaling factor and beta is a learned offset. The vector is not forced to keep values at a unit variance. It learns what scale and shift best serve the task. And the gamma and beta are updated during training just like any other way. Self-attention gave every token access to information for every other token. Each token representation has been updated and to reflect the relationship in a sentence. Now the feed-forward sub-layer process each of those updated representation, but this time with no communication between tokens whatsoever. Let's look at this. Here are 4 tokens sentence, right? Shown after the self-attention stage has been done. Each carries a representation that has been shaped by its relationship with the other tokens. Now they are about to enter into their own private rooms. Each token now has its own feed-forward box directly below it. Watch how the teal shaped box is moving across them, one at a time, processing each token independently. That's what this teal box is doing. There are no horizontal connection between the 4 boxes. Not one row, not one shared computation. The word the is processed in its own box. Similarly, cat, sat and mat are processed in their own respective boxes. What happens in one box does not influence what happens in another. This is the defining characteristics of the feed-forward layer. Position-wise meaning applied to each position separately. That's what this is doing. The label at the bottom says the weight W1 and weight W2 are same across all positions. The network does not have separate weights for the versus cat versus sat. The same transformation function is applied to every token, but it is applied independently, not jointly. This is the key distinction. Shared weights, but no shared computation. Position-wise is the precise term here. The formula that you see here is fnn of x equals max of 0 and x times w1 plus b1 all multiplied by w2 plus b2. This is a 2-layer neural network with a ReLU activation between the layers. X times w1 plus b1 is the first linear transformation. It expands the token vector into a higher dimension space. The max of 0 is the activation function, which sets any negative value to 0 and introduce a non-linearity there. Then W2 plus B2 project the result back down to the original dimension. The inner dimension after W1 is typically 4 times the model dimension. So in a 512 dimensional model, the inner layer is around 2048 dimensional. That expansions give network substantial capacity to store and transform patterns within each token representation before compressing it back down. We have now seen 2 sublayers in full details. Before moving on, it is worth naming the fundamental difference between them clearly, because the difference is what makes the whole architecture legible. Self-attention is a routing system. Its job is to move information from one position to another. When sat attends to cat, it is routing information from cat token into the sat token's representation. The arc in the mini diagram shows exactly that. SAT is reaching out to every other position and pulling in what it needs. The output of self-attention for any given token is a weighted mixture of all the token representation in the sentence. On the other hand, feed-forward network is a processing engine. Its job is not to move information between positions. It is to transform the information it has already inside each position. After SAT has gathered the context from cat, mat, and everywhere else through self-attention, the FNN applies a non-linear transformation to that enriched vector. The mini diagram here shows the 4 isolated boxes with only vertical arrows, right? Nothing connects them horizontally. Pure independent transformation, position by position. This sentence is worth committing to the memory. Attention routes, FNN process. These two jobs are separate, done one after other, and each is wrapped with its own add and norm to keep the training stable. The full encoder layer is this alternation: route, stabilize, process, stabilize. And understanding that rhythm is understanding the design. Throughout this video, we have been drawing the layer norm after the residual addition. That is called post-LN. The placement used in the original 2017 attention is all you need paper. Modern implementation often place it differently. This slide is about why the placement matters. Post-LN is on the left, styled in red. The formula reads layer norm of X plus sublayer of X. Looking at the mini diagram, you can make it as X enters the sublayer produces an output. That output is added to X through the residual connection, and only then the layer norm normalize the result. Normalization happens outside the residual sum. The output at the bottom state the consequence. At the large depth, this placement makes training unstable. The gradient flowing backward through many stacked post-LN layers can vanish or explode unless the learning rate is warmed up very carefully from near zero at the start of the training. The original paper used such a warm-up schedule, but it requires a careful tuning and becomes harder to manage as the depth increases. Pre-LN on the right is in teal. The formula reads X plus sublayer of layer norm of X. The placement has shifted. Layer norm now sits before the sublayer inside the residual branch. The residual path itself is completely clean. X flows around the outside without passing through any normalization. Look at the mini diagram. X enters, immediately passes through layer norm, then through the sublayer, and the result is added back to the raw X. Because the residual path carries a raw unnormalized value, the gradient flow back through the addition without interacting with any normalization. This makes gradient magnitude much more predictable across many layers, and pre-LN model trains stably at depth without requiring the careful learning rate warm-up that post-LN demands. This sentence is the key takeaway. Two formulas that look nearly identical, one with layer norm inside the residual branch and one outside, produce meaningfully different training behavior when you stack many layers. If you open a current implementation in PyTorch or Hugging Face transformer libraries, you will find pre-LN used as a default in almost all recent models. We have dissected every component of a single encoder layer. The final step is to see what full encoder looks like when you stack these layers on top of each other. Layer 1 is the foundation. It outputs Y becomes the input X to the layer 2. The interface is identical in both directions. Same number of tokens, same vector dimension in and same out. Layer 2 slides into place. Same 4 operations, different learned weight. Each layer has its own independent set of attention head, feed forward matrices, and layer norm parameters. Same architecture, separately trained behavior at each depth. Layer 3 and 4 appears here, and each addition layer gives the model another opportunity to find relationship that earlier layer were not yet equipped to capture. An attention head in a layer 4 can attend to pattern that only become visible after the transformation performed in layer 1 through 3. Layer 5 and 6 complete the stack, 6 identical bricks, each with its own learned weights assembled into a complete encoder. The output of layer 6 is the final contextual representation of a sentence. The sequence of vector that carries enough information for the decoder to generate an output. The original transformer used n equals to 6, that is n stack layers. GPT-2 uses 12 layers, GPT-3 uses 96 layers. The architecture scales by stacking more of the same brick, not by designing new kind of bricks. The brick itself has not changed since 2017. On the screen I have listed 5 questions. These 5 questions are based on the material till now what we have covered. These 5 questions will actually help you enhance your understanding of the material. I will highly encourage you to try it out. Pause and ponder, and maybe also put down in comments so that others can also get benefited by your answers. 1 encoder layer, 2 sub-layer, 4 operation repeated n times. That sentence on screen is not a simplification. It is the complete description, and everything else in this video is the detail that makes each of those words precise. Understanding 1 encoder layer means understanding the entire encoder, because the encoder is nothing more than this one block stacked. The architecture scales by repetition, not by introducing new kind of structure. That is the elegant part of the design, and it is also why studying 1 layer thoroughly is enough. In the next video, we move to the decoder block. The decoder shares the same 2 sublayers we studied here, but it adds a third, cross attention, where the decoder attains to the full encoder output while generating each output token. It also introduces masked self-attention, where tokens are forbidden from attending to any position that comes after them in the sequence. The mechanism that enforces the constraint that the model cannot see its own future output. If you're interested, do subscribe and see you in the next video. Bye.